All right, so now we are talking about, so we're going to continue talking about these Green's functions. As I had mentioned before, I had sort of given you or us a preview on what they look like for the Klein Gordon equation and for the Dirac equation. So let's get into the Klein Gordon equation first. Our solutions, so as we've said, we're looking for these special functions that obey the Klein Gordon equation that'll give us the potential of a delta function. So what that tells us, and so in mathy terms, or in math terms, this means that here's our delta function, and it's at some location x mu minus y mu, and that's our potential, and here's our special function s x mu y mu. And again, as I've said before, this special function it's going to be something that helps us understand what the interaction is between two points or two electrons. Okay. Now, what can we do with this? Well, we've proposed that this x mu minus y mu, equals this right here. So this is what I've said earlier in our other discussion. We have this normalization factor. Okay, and then we have this sinusoidal, or this oscillating function, k mu. Actually, let's do k mu, x mu minus y mu over k mu plus m. Put a minus sign right there. So we're going to propose that this here is going to solve this right here. Well, let's see if it does, right? So again, this is the Klein Gordon operator. This is our special function that has to obey this to give us a delta function. Okay, because again, we're treating electrons as if they're excited delta functions in these fields. And so, again, we're just going to do baby steps here, though. So the first thing I want to do is we're really just going to move, we're going to plug this in. We're going to plug this into here, right? So to do that, I can really just select, actually, I'll select and copy and paste. So here is our delta function. And then I'm going to copy this guy, copy and paste. And we have that right there, okay? So we can move this, or we can move this guy right here inside of the integral. So let's do that. I'm actually just gonna really move things around here. So I'm gonna move this guy, oops. And then I'm just going to put this guy inside the integral. So we've done nothing. We're just moving things around a little bit. And then what we can do is we can say, well, this right here, when it acts on this thing in here, we're really just going to get, this is all just a constant, okay? And what we get is that these derivatives, when they're acting on our spatial components, remember these are derivatives of our spatial components, we just get the k mu out. Right, so this is going to come over to this derivative and likewise to this derivative. And so what we end up getting, and we have this minus sign also. So what we end up getting is, I'll just erase these guys. We get the k mu, right? And because of the I, that doesn't really matter that much actually, but you can see that I times minus I, that's going to give us, well, I times I believe that's going to be -1, right? Because we have minus I times negative I, well, I times I is -1, and then we have 2 minus signs, so that's going to be minus, so it's going to be -1, right? So we have this negative sign out here, and so when now we can see that, and actually we want to square our mass term in here. Again, the mass is just a constant. And so what this gives us is we're able to cancel these guys out. And when we cancel those guys out, we get d4k times 2 pi 4 times e to the minus I k mu x mu minus y mu. Okay, and what we're doing is we're saying, well, is this equal? Are these two equal? And so, well, are they equal? We can say as a definition actually that these are equal. What this means, we could take a look at this actually. If you're at all familiar with Fourier transforms, this is equal to our delta function, because what this is a Fourier transform. So a Fourier transform essentially is a way from going between spatial space to sort of temporal space, if you will, or frequency space. Now that might mean nothing to you right now, but let's go over Fourier transforms a little bit. So Fourier transform, suppose now, so I'm going to diverge about Fourier transforms. And so what is a Fourier transform? A Fourier transform is something that enables us to take any sort of shape, right? It can be, say, a shape like this, and convert between sinusoidal patterns. And actually, to be a little bit more clear, the way it does this conversion is it takes the frequency. So suppose we had something that looked like this. This looks like a regular sine function with a single frequency to it. Well, that frequency can be mapped again by a Fourier transform into a single peak, the location of that peak being at the frequency, on the frequency axis. So this frequency is the frequency of this wave. And so where this is space, this here is frequency, and you can interchange between the two by Fourier transform. Okay, this is perfect for us because we're treating particles as these peaks right here. We're treating particles as excitations in these fields, Mathematically speaking, we are saying that these particles, as excitations in these mathematical fields, are delta functions, exactly what this thing is. It's a delta function in some Fourier space. Or not in some Fourier space, in the actual space. So this is actual space, and we can convert into the Fourier space. And this conversion into the Fourier space, well, this is what the Green's function it does, right? So we're talking about a particle. And when we talk about a particle, we can talk about it in terms of its delta peak, right, or its delta function. Or we could talk about it in terms of the frequencies that are required to make that delta function, okay? And so, and this, again, this all ties into this potential, right? This potential here is a delta function, right? So this is what our particle looks like. It looks like a delta function. So we can look at this equation. And we can take note that an actual Fourier transform, mathematically speaking, looks very similar, right? So we're going between two different modes, or two different spaces, mathematical spaces, one in frequency space and again one in momentum space. And this is just, we're using dummy variables here, but a Fourier transform, again, looks like this kind of where our integrand is this t, and it shows up in our exponent, and whatever that's being multiplied by right here shows up right here, right? Well, we can see the same exact thing right here. So here's our k, and here's our what it's being multiplied by, and our argument right here. Okay, so this is actually true, right? So this mathematical statement that this is a mathematical statement saying that the Fourier transform is a sum of waves, right? So this is waves over a bunch of them, right? Because we're summing over different waves with different momenta, with different values of momentum to get a delta function, okay? I want to diverge, I want to talk a little bit about these Fourier transforms a little bit more, because I think they're very interesting. And I think this is a good primer on sort of the philosophy behind QFT, and also the philosophy behind many other areas of science, including the type of science that I am doing my PhD in, which is biophysics. And I do want to go into this a little bit. This is very, very interesting. The idea that we can take, we'll go up here, the idea that we can take any complex thing, right? Suppose we had 2 delta functions, or maybe 3 delta functions. Well, if we had 3 delta functions, we can construct these 3 delta functions using a combination of sine waves or cosine waves, or however we could shift the waves, we could shift the amplitudes of the waves. And again, the way we do that is, if you take a sine wave, here's a sine wave, that didn't look too good. If you take a sine wave and then take another one, say, that looks like this, well, at this point here, say, like here, right here, we're going to get these two values adding up to each other, right? And when they add up to each other, we get a value that might be up here. Okay, and then say right here, well, we're going to add these two values together on the black and the blue lines, and we might get a value right here. But then we have, say, at this point, right, we have an extremely negative value and a somewhat positive value. Well, we might get a point that looks like it's down here somewhere. Okay. And the idea is that you take multiple waves, just like we're doing in this right here. Just like we're doing right here, we're taking multiple waves, okay? These are the waves. This is taking into account multiples of them, multiples of them. And we're adding all of them up so that in some areas they'll constructively interfere, and other areas they'll deconstructively interfere. And what you can end up getting are extremely localized peaks, right? You get extremely localized peaks where you can construct something that, say, looks like this. And then if you add more and more, you can get a localized peak that maybe looks like this. Okay? And you can keep on adding higher frequency waves, and you can phase shift them around to get a peak anywhere you want. And you can get multiple peaks anywhere you want also. So the idea, again, is that this object, this special function right here, takes the form of a Fourier transform, okay, to give us a potential that looks like this. So the idea, again, in the book, again, we're going off of this book, No Nonsense Quantum Field Theory by Jacob Schwittenberg. He doesn't go into Fourier transforms at all in the book, but I think they're necessary to go over, so I'm going over them. In this book, he talks about these being, he provides a picture that looks like this almost. It looks like, you know what? I can refer us to the page number in this book, actually. If you have the book, it is on page, let's see here, that's quantum fields. We're still in classical fields. So these classical fields are, that's quantum mechanics. Almost there. Let's see. I know there's, okay, here's the picture. It's on page 242. And he says, basically, so our potential, again, is a spike function. The spike function tells us something about the interaction between two particles. So you have, and again, this isn't the shape of the field itself. We're looking at an interaction, right? So the potential, again, this is the potential, is a delta function. And that delta function is constructed by these by this special function, that we're calling a Green's function. And we apply the Klein Gordon case to this function to give us this type of potential, okay? The way this is pictured in the book is that he says, okay, you have two particles in the field. So here's our field. You have two particles in the field, and you have this Green's function, right? So you have some potential here, and you have some potential here, and this Green's function is going to tell you, or this special function tells us, this special function tells us, so here's some potential. The special function tells us something about the interaction between these two particles. Okay. So that really is the idea behind these Green's functions, or the idea behind these delta functions also, right? So the Green's functions, again, are things that are going to help us describe interactions between particles, because we're treating the particles, again, as these delta functions, and we construct those delta functions by means of a Green's function that obeys the dynamics of the field, okay? And what we'll see later on is that these Green's functions, they will take on sort of a life of their own, right? We have to sort of constrict them to obeying the dynamics of these fields, right? The Klein Gordon dynamics, or the Dirac dynamics, or the Proca dynamics. But we're going to see that they all take this Fourier transform-like behavior, where in one space we have particles that are treated as excitations, and in the other space, like that we've talked about in this momentum space, or in this spatial space, we're talking about a construction of sine and cosine waves. Okay, so I'm just going to reiterate that one more time, right? So, because I want to get this in our heads as best as we can. So we have particles, right? So we have particles that are excitations in these fields, and these particles, these particles that we're drawing right here, they're excitations in these fields, and these fields are constructed by these Green's functions. And these Green's functions are telling us something about the interactions between these two particles, okay? And I'll go a little bit more into this, actually, because, again, this is super, super interesting, especially when you're doing stuff, especially if you go into, say, biophysics, right? Because Fourier transforms, you can take a super, super complicated field, if you will, and you can Fourier transform that to figure out what all of the quote-unquote sort of details are about that field. I'm sort of going around this a little bit haphazardly, but in the cryo-EM world, what we do, right, is we take electrons, we bombard electrons onto proteins, and the proteins will give us this scattering pattern, or not really a scattering pattern, but they sort of give us this these peaks, right, in the electron wave, and then you could perform a Fourier transform on those, and what you get is, what you get is essentially a reconstruction of your protein image, and then you can blow that up and you get this map that looks exactly like the protein. That's sort of the rundown of cryo-EM, and we're kind of doing the same thing here, where we're saying we have these particles right here. I'll just erase this a little bit. We have these particles. These particles are excitations in this field, right? They're excitations in this field, and we can decompose these into the essential Green's functions, that make up these delta functions. And when we do that, we're getting how these things interact with one another. So if we had like 2, 3, 4 peaks, we can decompose that into its Fourier into the Fourier transforms using the Green's functions, where the Green's functions are essentially Fourier transforms. We can decompose that into the essential waves that make up the field as particles are interacting with each other. Okay, and that's what these are, right? And we're gonna be seeing that this is the same thing for the Dirac field. This is the same thing for the Proca field, and yeah. And I think before I go, I just want to hit this home one more time. What we're doing again is we're Fourier transforming. So in this space we have waves. Now I'm not going to be, and these waves are going to tell us something about the interactions, right? So, you know, that was really haphazard, but we're going between, again, momentum space and position space. And so in one case we have position, and the other case we have momentum space. And the reason I'm trying to hit this home multiple times is because if I've said something that confused you once, hopefully one of the other times that I've said, hopefully that doesn't really confuse you as much. But again, the point that I'm trying to get across is that we can interchange between position space, momentum space using these Green's functions. And these Green's functions, again, they obey the dynamics of the fields that we're interested in. That's really all that is. And these Green's functions are what describe the interactions, because waves will interact with one another, right? And so that's why these Green's functions are very important in describing interactions between particles. The book doesn't go into this that much, right? The book says, you know, we're just going to say that the Green's function is what tells us something about the interactions. Well, if you go a little bit deeper into that, the interactions really are taking place on the level of waves, because waves are the things that interact with one another, not the delta functions, right? The delta functions are just standalone functions. The only way you can say these standalone functions are interacting with one another is by decomposing them into waves that actually do interact with one another to create those peaks. And so there is logic behind this, and the book doesn't go that deep into it. It doesn't go that deep into the logic. And so I think it's important for us to understand at least why these Green's functions are essential in talking about interactions. With that being said, I'm pushing on 30 minutes. If these are videos you like, please decide to support me on Patreon. Hit that subscribe button, and I will see you guys in the next one. Bye.